So thanks, Lucia, and also thanks to the organizer. And also thanks to Carlos, because he did all the art part of the job by providing the technical part of this topic. So I want to start more or less from where Carlo started. So because the idea is to use all this machinery in order to provide, well, not yet a solution, but at least a strategy to solve one of the most classic problems in nonlinear elasticity. So as before, we have a body in a certain referent configuration omega. We do a deformation, so we impose some boundary condition given by a function g, and now we want to look for, to search for minimizer of this neo-Hookean energy. Okay. Now, as Carlo said before, problems of this type are largely studied, but in this specific case, the particular grow, because we are in dimension 3 and we are looking for a quadratic grow, makes the standard machinery of calculable variation in general not useful. So as first things, let me provide a state of the art of the situation, okay? So this is the situation. We know that for that kind of energy, or something similar also with polyconvex energies, when we are in dimension 2 and we work with energy with a p grow strictly larger than 2, or we have a certain control of the minors, or a lot of other additional assumption, we are in position to use the standard calculus of variation machinery and provide the existence of minimizers. On the other hand, when you arrive to the limit case p equal 2, well, then it's a mess, because the contraexample provided by Conti-De Lellis. It's a very nasty contraexample. In a certain sense, this contraexample provides an obstruction to the standard method. Now, just 2 days ago, Anna and Stanislav show us a very nice improvement of the situation that more or less complete this site. Because on one side, they managed to improve the Conti-De Lellis contraexample by showing that also if you have a little better control of the determinant, still the pathologies that the Conti-De Lellis example provides are still there. But on the other hand, by showing that if you improve it just a little, so if you have the in condition plus a little control on the determinant or a control on the distortion, then you can provide at least a sort of compactness and lower semi-continuity. Okay? So this, in a certain sense, complete this part. What is open still is, okay, if you start with the family of the homomorphisms, as Stanislav did, well, at least you have to figure out, because you can provide solution only in the closure, so you have to provide a characterization of the closure of the homomorphism in this setting. It can be hard, but this will be probably very technical, and that's it. Or you can try to enlarge this result by considering not just homomorphism, but more generic function that just obey to the if condition and this other condition. This can be a little bit more complicated, but as you see, you are there, okay? So this part is almost done. So thanks. Now, what we can do? Well, then, sorry, we have to move on to the side. Now, the fact that there is this obstruction and that you cannot use the standard machinery does not mean that there are no solutions for the neo-Hookean energy. It means only that your standard machinery does not work. However, there is the possibility that this contraexample, indeed, from the energetic point of view, use too much energy, so in the minimization process could be ruled out. So it still may be possible, and we hope so, because it's a model that should describe the physical world, it should be still possible to find a solution for the neo-Hookean energy, okay? So now what you do when your main tool, so the standard machine, does not work? Well, or you change job, or you pray, or simply you relax, okay? Relax, it's fine, huh? No, you relax from the mathematical point of view, okay? This is something that already, where is Aldo? Aldo, yeah, there. Aldo suggested you during his talk. So what you do is just, okay, your functional and your family of functions is not good enough. You have no compactness, you have no lower semi-entity, okay? You enlarge your space, and you also change a bit your functional. So in Aldo's case, it was okay. We are looking for optimal solution from the perimeter for the perimeter point of view. So we are looking for sets. Well, we cannot find a solution, so we look better for functions, well, or also measures. Okay, so you enlarge all, so that what before was an existence problem, it becomes more, because in the new setting, probably you have existence. What you have to do, you have to recover from this new solution a solution for your old problem. In Aldo's case, was from a measure, you have to recover a set. Here will be something similar, okay? You have to recover and to have a nice function that is in the setting of the Sobolev W12. Okay, now how much is easy to relax the neo-Hookean energies? If you follow what is Francesco instead, there. If you remember Francesco topic, seminar, he provided a representation. So it's always possible maybe to relax a problem, but then you have to provide a representation, an integral representation. In Francesco seminar, we saw that the condition to have an integral representation, it's really delicate. And indeed, as also Stefan pointed out, in the case when there are constraints on the determinant and so on, in general, our representation is almost impossible. So what you can do, if you want to try to relax the problem, maybe it's better that you immediately provide a candidate that is explicit, and after you just hope that is the right one. This is what I'm going to do. So I'm going to provide a possible candidate that relaxes the neo-Hookean energy. It will be, of course, explicit. So, first of all, let's see the starting point. So, what is the standard family of functions where we are looking for a solution? Then we try to enlarge this family and also, as I say, to modify the neo-Hookean energy. So the standard family is this. So at the family in W12, we require that there is a uniform L infinity bound, so all deformation has to be in a big box that match some boundary condition. And of course, since I'm looking for physical solution, I'm also asking that there is no interpenetration, and there is also orientation preserved. So a map has to be 1-to-1, and the determinant has to be positive. Okay? Now, I want to simplify my life. So for this part of our research, we also required that no cavities are allowed. So this was the object that Carlos introduced before. It means just that there is no creation of new surface along the deformation. Now, let me Now, let me go back to the Conti-De Lellis counterexample. This is precisely the same slide that Carlos used before. What I want to show you is more how the sequence of deformation of the Conti-De Lellis provided a very strange effect. Why it is? Now, in order to provide a relaxation of the neo-Hookean, I want to think in a similar way that, I mean, when you try to relax an energy in W11 and you have just one coercivity, okay? You know that in general there is a problem because you are working 1-1, but you have no compactness. So you know that in the limit there is the possibility of a singular part. So in order to relax your energy, what you do is just you add the singular part, right? Now here, well, here you can't use this because the deformation are regular enough. On the other hand, in the last years, a lot of results use the fact to go and to work in the deformed configuration. So instead to work with the deformation starting from your domain, the reference configuration omega, you go in the deformed setting and you work with the inverse of the deformation. So maybe the key is just to look to the inverse and check how bad can become the inverse. So maybe the concentration and the problem are located on the inverse. And it is so. So this is one of the members of the sequence that in the limit provide a strange effect. So here there are the two dipoles, so, and what you do is this. You create a small cylinder and two small caps, two small hemispheres of size epsilon. Then you do this. You simply stretch in this direction and do a compression. So you are transforming this object. So the C, it becomes this part here. These two small hemisphere becomes this two big object. So from the volume point of view, you are not doing disaster, so there is a descent control. You are more doing a disaster from the stretching point of view. But indeed, you have not a control on the cofactor. So you can do this. Now, what you do, by sending n to infinity, you relate this n to the size of this cylinder. So you send n to infinity and set to the cylinder to 0. So more or less, these three objects are collapsing just in a surface that include a large hemisphere on this side. So you have this at the end. Now, let's see what happened from the inverse point of view. So let's do deformation from here to here. Let's see the inverse from here to here. So you are approaching a point here. When you approach from this side, where are you going? Well, you are approaching in the sequence you were approaching. So this, so you are going here. And instead of on the other side, we approach this surface from this side, we're going here. This means that the inverse, so the limit of the Conti-De Lellis counterexample, has an inverse that is SBV, as Carlos said before. Here there is a full jump. And the amplitude of the jump is precisely the distance between the two dipoles. So the inverse is not regular, it's SBV. And in order to relax our problem, we have to add this concentration. Let me say that, as Carlo said before, okay, this was just a bit more what I prefer. This is, I mean, a similar behavior is in the Steinitzer and Anna counterexample. Okay, in that example, that sort of onion, what you do, you have part of these circles in trying to envelope one part of the initial configuration, just collapse in one single line. So it's a line that is located here. I just copy from that paper. I have no time to redraw all. And again, when you go from this direction, you finish here. And when you go from this other direction, you finish here. So again, the inverse is SBV. And again, there is a jump set with a fixed amplitude given by the distance between the two dipoles. Now, before to be a bit more precise about the relaxation and the space where I want to set up these new functionals, let's see what we have from the initial model. So we are working since okay. First of all, I will work in the axial symmetric case. Well, because it's just easier. But on one side, it's not a stupid condition, because from the physical point of view, a lot of models are just, axial symmetric. Also, the sample that you saw in the previous talk was just a cylinder, okay? So that, and on the other end, all these two counterexamples that we have are both axial symmetric. So maybe it's better first to try to solve the axial symmetric case, and then maybe we try to move to the more general case. Already the axial symmetric is a bit a disaster, let me say. So in the case of the axial symmetric, of course, you can use cylindrical coordinates. So more or less, you have a bidimensional description, and when you describe your problem with these new two coordinates, you see more or less you remain a neo-Hookean energy, and at least when you are a bit far from the axis, all looks fine. So what I want to say is that so when you look to the, you can see this as a bidimensional problem, a bit far from the axis, is like the neo-Hookean problem in dimension 2 with growth 2. This is very good because it means that you are extremely regular. So the things far from the axis goes well. So the problems comes from the axis, okay? So now let me be a bit more precise about this relaxation. So what we are looking for? We are looking for a set a larger space C that would be compact and contain our initial family ARS. So the space of the function that are axial symmetric and regular, as I defined before. And now I want also an effective energy F defined on C that extend the initial neo-Hookean energy E. And what I want is this. I want that the infimum of the neo-Hookean on the old space coincide with the minimum on the new space and the new energy. So before, I had only an existence problem. Now on this, I can provide a solution. So what I have to do is just then show that the solution on the new problem is also a solution in the previous one. By showing that it is regular enough so that, for instance, all these pathologies does not appear. It's like when you work and want a solution in W11, First you find a solution in BV, then maybe you prove that the solution is regular enough, so it's a solution of your original problem. So what about this, what is the candidate for the space C? So as space C, where to set my new energy, I take the weak limit, the weak closure of the space ARS. Okay? Of course, defining this way is too abstract. We want a better characterization. And these are some of the property of the function that belongs to this space. Some of them, already Carlos say something, but let me just to recall what I need for the following part. So, of course, this map are still axial symmetric. That is a condition that is strong enough. The topological image coincide with the initial deformable configuration omega prime. So in particular, the topological image of the axis is as zero measure. Now, what is really nice is the fact that the two components that are perpendicular to the axis are regular. This is not so strange. Why? Because I told you that nasty stuff comes from the axis. Now, when you look to these two components, and you look to the inverse, so the inverse is taking all and bringing back, okay, if there is something nasty, is coming from the axis, so these are bringing back to the axis, but of course, since it brings back on the axis, there is no discontinuity in a certain sense. So the real problem is in the component that is parallel to the axis. Now, what we know is that in the limit, the inverse is PV. And why is in PV? Well, this is very easy to show. Well, we know that in the original space, the inverse is Sobolev. Of course, we can control with the gradient, we control the cofactor, then we pass in the deformable configuration. So you have L1 control of the gradient, and so you know that the limit is in BV. But we know a bit more. We know that when you are far from the axis, you are regular because the axial symmetry and the regularity in the bidimensional case. So all the singular part of the inverse is concentrated on the topological image of the axis. Good. Now, let me provide a lower bound for the neo-Hookean energy. So we will see the appearance of new P's that I will use in order to define my relaxation. Okay? So what I'm claiming is this. So we have sequence in W12 living in the initial space. I want to show you that it's not just through this. So it's not that you control the gradient with the gradient, but you have this more. So this additional energy given by the concentration in the inverse. This was your question for Carlos. Okay? Okay. So, what will be my candidate as relaxed energy? I will take just the neo-Hookean, and we'll add this term given by the singular part of the inverse. Plus, this two is sharp. Well, indeed, it's a bit fake. Indeed, it's the singular part of the third component of the inverse, and indeed is concentrated on the topological image of the axis. Right, this is true? Okay, I will give you 2 proofs. One is completely fake, but maybe it's easier to understand. And then the other, it's true, modulus technicalities, but it's a bit a mess. So what we do this. So it is very easy, okay? So we take the sequence, and we divide, we split the domain in 2 parts. Inside a cylinder of size delta, close to a cylinder along the axis of radius delta, and outside, okay? Now, for the part that is inside, what we do, we just control with the gradu square, we control the adjoint or the cofactor. Just pay attention because we are just controlling one component, and why? Because if I control all, then I need square root of 3, and here I need instead, I want a better things, I want 2, not square root of 3, because it's a bit better. And I will tell you why this is fundamental. Then what you do, well, the usual game that I was telling you, well, not so usual. So we work in the deformed configuration. So we pass in the deformed configuration. Then we pass to the limit in a certain sense. This go to the gradu on this domain. This morally is going to the full gradient of the inverse. Now, when you shrink delta to 0, here you recover the full gradient of u. Here instead, what you get is the part of the gradient of the inverse concentrated on the image of the axis. But I already told you that there is fully concentrated, so it's fine. It is a fake proof. Well, it's a fake proof because you see, if you work in this area, but you have always to pay attention when you do this about the integration, where you are integrating. When you move to the deformed configuration, luckily, in the deformed configuration, of course, your domain is moving with the sequence. So what we have to do, generally, is to show that your deformed configuration here are in a certain sense stable. In this case, it's not possible. It's not possible because you have not you are not a good control of the distance from the boundary of the cylinder. Okay, this is a phenomenon that you can also see when the grow it's larger than 2. When you work in the deformed configuration, there always the risk of a pinch, so you cannot really control how this object change along the sequence. So here you have to be a bit more precise, but okay, this is technical. If you are interested, then I can show you the real proof. Now, why is it, so we provided this result. First of all, let me say that this new functional, this functional f, indeed is semi-continuous, but here you can prove this inequality, not just when you have a sequence into regional space, but when you have a sequence in the closure, but just adding also on this side, this part. So this is really the good candidate. But why is sharp? Because of course, at the moment you have just something that provides a lower bound, be the best lower bound. Otherwise, there is no hope that this is the relaxed version. Now, well, it's sharp because until 3 days ago, this bound was capable to capture all the possible counterexamples on the market. There was just one, there was just the Conti-De Lellis counterexample. For that example, it works. We don't know if it also works for the new counterexample. I hope so. So What about the Conti-De Lellis counterexample? See, what you can prove, you have to take the Conti-De Lellis counterexample, the paper, and then you have to add maybe 10 or 10 pages of computations, because in that paper they just provide a bound for the energy in order to show that there is convergence. Here you have to do something better. You have to provide the exact number. This is also why we didn't check the new counterexample, because probably it need more than 10 pages, and so I trust that it's the right. Okay, so if you do the computation, what you see is the gradient square, go to the gradient square, 2 pi. Okay? More, the 2 is precisely, the pi is precisely the singular part of the limit. So for the Conti-De Lellis, the energy that we provided is the sharp 1. Of course, our hope is that for any possible configuration, this remain sharp. Of course, to prove this, every time that you give me a function in the closure, so every time that you give me a function in this space, I have to provide a sequence in the original space so that the convergence of the energy is with an equality. How much this is hard? A lot. We are still working on that. Okay. What is nice about the energy that we provide is this. As Carlos said, when in the limit the surface area is bounded, then our inverse is not just in SBV, is not just in BV, but in SBV. It's nice because by using some work of Ambrosio, then you can prove this structural theorem about the singular part. The singular part is precisely given by the distance. I mean, what you know that there are a countable, maximum countable number of dipoles, and then is given by the distance of the dipoles for the surface of where there is the discontinuity. And this is precisely what happened for the Conti-De Lellis counterexample, and I think also in the new counterexample. Of course, to have why is important to have this kind of description? Because also assuming, I hope, that we will be in position to prove that our energy is the relaxed one for the neo-Hookean, then you have, when you have a minimizer for the new energy, you have to go back. You have to show that, that your minimizer in the larger space is still regular enough, so I have no concentration in the inverse, and so it's a solution of the original problem. Well, it's easier to work with objects that are in SBV, because with the counterpart it's a mess, it's a really mess, and with an energy that is a nice description like this. Now let me, how many minutes? 5, be fast. So let me now conclude. It's a trick. So open problems. For sure the full case is open, so feel free to try, all yours. As I say, we don't know if our candidate is the correct one. We have to provide a recovery sequence in any case, not just in the Conti-De Lellis. What about if we had, I mean, if we allow cavitation? Also, we don't know this, because with cavitation, it's really harder to figure out how the bad parts are going. What about the inf condition? So we know by the Conti-De Lellis that the inf condition is not preserved. It's preserved if you have enough regularity on the inverse. Now, but if the inverse just converge and the limit is Sobolev, is still the preserved? The sensation is yes. Why? Because if it's not preserved, when you manage to put material inside a ball, okay? But to do that, you have to create this jump. So maybe if in the limit you're still Sobolev, you cannot do this sort of inclusion, and then you should preserve him. We think that it should be so, but then from the technical point of view, you have to prove it. And finally, the question that you were raised before, are we really sure that I mean, it's possible that there is, in the limit, you have a BV, a pure one, and not just SBV, so that there is a Cantor part. This happens when the new surface energy goes to infinity. Well, the answer is 2 minutes, 1 minute. Okay, the answer is maybe. We are still not a real counterexample, but an idea. And this is maybe if you work in BV, you should know that when you touch SBV, you can also touch the real BV. So when you have the possibility to do jumps, also the possibility to do Cantor parts. And we can use this idea in this way. So this again was the Conti-De Lellis counterexample, okay? You have a dipole, you collapse and use these two dipoles to include one of the two hemispheres in the other. But it's possible also to have a couple of dipoles, easy. So you include this in this, and then this in the other. And 3, 4, 5, infinite, yes, you can do that. So there is the possibility, but we have to do the computation to see if the energy remains bounded. So you can do this game with an infinite amount of dipoles, and instead to have jump, you create a devil star case, so you create a Cantor part. So instead of a sharp jump as here, you create just a Cantor section. This is a possibility. It's not still a counterexample because we didn't do all the computation. So for the moment, it's just an idea. And this is enough.